Okay, folks, here we go. Welcome to Corona Physics. Okay. First, I intend to change a little bit from what I had said in the introductory video, and that is that assignments, instead of being due at the midnight of the day they're due, I'm changing that to noon on the day that they're due. So the review assignment that I just moments ago posted on RenWeb and on Google Classroom, and that I believe I also emailed to everybody, that assignment, that first part of the Chapter 10 review assignment, is due tomorrow, which is Tuesday at noon. If it's not submitted to me by Tuesday at noon by email or through Google Classroom, it will be counted as late and we'll lose credit. All right? All right. Now, I want to back up first and do a little review of the basic concepts so far in the chapter. Projectile and satellite motion, this is chapter 10. I'm currently looking at page 178 and just remembering this. What is satellite motion? What puts an object in orbit? It's basically when an object is thrown so quickly horizontally that as its curved path works its way downward, that curve matches the curve of the Earth. And as you know from our previous discussions, that occurs at a speed of approximately 8,000 meters per second, otherwise known as 8 kilometers per second. And that's someplace in the vicinity of 17,500 miles per hour. And that works because the Earth, as the Earth curves, it drops, as the Earth curves, the Earth itself drops 5 meters for every 8,000 meters, and that's the same distance that an object will fall in 1 second. So if it's moving 8,000 meters per second, in that second it will fall 5 meters, but so does the Earth, and therefore it'll never hit the ground, provided it's above the atmosphere. There's no such thing as being above Earth's gravity. Please remember that for the test. Where can you go to escape Earth's gravity? No place. In fact, at the altitude where the space shuttle, wrong, at the altitude where the space station flies in orbit around the Earth, it has about 90% of the gravitational force on it from the Earth that it would have if it were on the ground. So it still has gravity. If it didn't have gravity acting on it, it would go in a straight line. Okay, all of that is reviewed. If I project an object sideways while at the same time releasing one vertically, like this, their paths will be very different, but they will both hit the ground at the same time. Why is that? Because the horizontal and the vertical motions are, what's that word? Yes, I heard you say it, independent of each other. The horizontal knows nothing about the vertical. The horizontal remains, give me the C word. Yes, I heard that right through the airwaves. Constant. The horizontal speed is constant, ignoring air friction, while the vertical is, of course, accelerating at 9.8 meters per second squared. They are independent of each other. Put those two together, the constant horizontal with the accelerating vertical, and you get that familiar curved path. This is all review. By the way, all of this is in the book. Paul Hewitt says it better than I can. Read the book. I'm skipping ahead now to all the way to page, on 182, he raises that very interesting point that we've discussed in class extensively, and that is that if you fire an object at a given speed at, say, a 60-degree launch angle, and you fire another object at the same speed at a 30-degree launch angle, they will hit at the same spot. This one will take longer because it has to rise higher, This one will be in the air for a shorter time, but they will hit at the same time. By the way, speaking of air, this is assuming no air friction, of course, as we so frequently do, because if we take air friction into account in everything, we would get so bogged down in details that we would never get anywhere. So we will pretend there's no air friction in that. I'm flipping ahead now to a very important concept. Oh, by the way, I've discovered that there is a mistake in the book. Paul Hewitt seems to have told us something that's just plain not true. Near the page, bottom of page 187, he states that when they're putting an object into orbit, they first launch vertically, and when they get outside the atmosphere, then they turn the vehicle and then go sideways into orbit. Wrong. They do not do it that way. It's a nice smooth curve all the way from launch to orbital insertion. They don't go turn. No. They go more like this. Just thought I'd throw that in there. Is that critical for the test? No. It just bothers me that there is an actual error in the book. What's special about that altitude of 22,300 miles? You may recall, that's where you have to put an object. If you want its orbital speed to exactly match the rotation of the Earth so that that satellite always stays over the same spot on the Earth. Pretty cool concept. That way, if you have a satellite, a communication satellite, a TV satellite that's out there at 22,300 miles, you can point your satellite TV antenna at it and it's not going to move. Because it's rotating with the Earth, it's going to always stay in the same place, provided it's over the equator. That's all explained here on page 187. Why is there something special about that distance of 22,300 miles? Because distance determines orbital speed. The farther away the object is, the slower its orbital speed. Remember, the space station, it's only up about 240, 250 miles. It's very close to the Earth. And its orbital speed, it goes around the Earth once every 90 minutes. Its orbital speed is only, well, no, I shouldn't say only, it's a whopping 820 or so miles an hour at our latitude anyway. At the equator, it's about 1,000 miles an hour because it's so close. By the way, the moon, someplace in the book here, I wrote myself a note, I have no idea where it is now, that the moon's orbital speed, because the moon is so far away, I don't know where that was. I think we must have mentioned this back in the previous chapter. The moon's orbital speed, if I can't find it in just a moment, I'll give up instead of wasting your time. It's back there someplace. The number 2,300 pops into my mind. It's much slower than orbital speed of the space station, which is about 17,500 miles an hour. Okay, let's move on. That's all review. We said just last Friday, we emphasized that on page 188, all orbits are, give me that E word. I didn't hear anything, try that again. Give me that E word, all orbits are, yeah, I heard 3 people whisper it, elliptical, where the object being orbited is at one of the 2 focal points. So you've got a focal point there, a focal point there. You've got your orbit here. Oh, that's terrible. It's good enough. If this is, say, the Earth, the object being orbited is at one of the 2 focal points. The other focal point is, abbreviation ES. Yeah, I heard that. Empty space. There's nothing there. I want to neaten up this ellipse. That's just awful. Let's see. From there, we define some special points. I'm now flipping already over to, where am I flipping over to? I don't know where I'm flipping to. I'm someplace around 192 or 193. I'm not sure. The point where it's closest to the Earth is called what? perigee. The point farthest away from the Earth is called apogee, and that's only if you're talking about Earth. If you're talking about the moon, it's perigee and apolloon. If you're talking about the sun, it's perihelion, and I think it's pronounced aphelion or aphelion, I'm not sure. What else did we discuss? Oh, for the test, you have to know where is perigee, where is apogee. How do you remember that? A for far away, perigee for pretty close, far away. At this point, as we discussed in class and as is clearly indicated for you on page 193 in the sidebar, at this point we would have minimum potential energy. Why? Because potential energy is a function of how close it is to the Earth or how high it is. Well, here it's the closest it's going to be. The closer it is, the lower your potential energy. So that's minimum potential energy. It also is maximum kinetic energy. That's where it's moving the fastest. Then it's going to swing around here, pulling away from the Earth, therefore slowing down. So here we have the kinetic energy is decreasing. I'll just do DEC. While it's getting farther away from the Earth, meaning its potential energy is, increasing. And at apogee, what happens? At apogee, it has maximum, which one? Yeah, that's right, maximum potential energy. And it has minimum, oh yeah, I heard that, not exactly what I'm looking for. It is indeed minimum speed, minimum velocity, but the word I'm looking for is minimum kinetic energy. Both answers are correct though. Over here, as it's traveling this direction, by the way, we are going that direction, over here at this point, it would have decreasing potential energy because it's getting closer to the Earth, and increasing kinetic energy because it's speeding up. And then the whole cycle keeps repeating itself like forever. Pretty cool concept. If all orbits are elliptical, how could you have a circular orbit? Yes, remember, a circle is nothing but a special kind of ellipse where the two focal points happen to be at the same place. And that would make a circular orbit. Okay, in a circular orbit, no work is done on the satellite by gravity because the direction of travel is always perpendicular to the force of gravity, so no work is done. But in an elliptical orbit or a non-circular orbit, work is being done. As it's coming around this way, it's doing positive work. This is something we did not discuss on Friday. Coming around here, we've got positive work being done because the force is in the direction of travel. Out here we've got negative work being done because the direction of travel is opposite the direction of gravity. Negative work causes what? Negative work causes a decrease in kinetic energy, just as positive work causes an increase in kinetic energy. It all fits together so nicely. This is all review so far, well, except for that little detail. It's the only new concept I just threw in there. Now, that brings us to the totally new stuff. In case you want to fast forward or something to the new stuff, let me write this on the board in big bold print, that this is now the new stuff. And it's coming from, I'm starting here on page 194. Page 194. Ta-da! Okay, new stuff coming. All right, here it is. Escape speed. What happens if the space station, which is orbiting at a speed of about 17,500 miles per hour, what happens if it speeds up? If we were to fire its engines, it does have some small engines for course corrections. If we fired the engines and sped the thing up, what would happen? as it's orbiting the Earth, it would speed up and try to shoot out. But as it shoots out, something interesting happens. Because we sped the thing up and made it shoot out, it's going to end up moving more slowly now. Why more slowly? That doesn't make sense. Because it was rising, and as it rises, like anything, when it rises, it's going, whoa, I hit the projector. I hope everything's okay. As it rises, it's going to slow down. So it actually slows down, and it will go into some slightly different shape orbit. If they want to stay in that higher orbit, they first have to speed up to shoot out there, and then they have to fire the engines and speed up again, because they slowed down so much as they rose, to insert themselves into the higher orbit. But the funny thing is that that new higher orbit is now going to be at a slower speed than it was before. Oh, it could give you a headache. It's all so weird. I'm glad NASA knows what they're doing. But again, remember, the farther away an object is from the Earth, the slower its orbital speed. So if they change their orbit from here to out here, the final result is they'll be orbiting at a slower speed now. Let's see. Oh yes, so my point about escape velocity. What happens if, would it be possible to increase your speed so much that you go into not just an elliptical orbit? What happens if you go so fast that, and the best way I can think of to put this, what if the ellipse breaks open? Yes, it happens. It can happen. We make it happen. We want it to happen sometimes. If that ellipse breaks open, what that means is you're now moving so fast. Remember, as you get farther away from Earth, what happens to the force of gravity? It gets weaker, dramatically weaker. It's that inverse square relationship for distance. As you're getting farther and farther away, gravity is getting weaker. It's trying to pull you back, but it's getting weaker all the time. You're moving so fast outward, though, that the force of gravity is weakening at a rate that it simply can never pull you back in again, long story short. That speed is called escape velocity. For the Earth, escape velocity is 11.2 kilometers per second. Escape velocity from Earth, escape velocity, oh, I love that movie, Finding Nemo. You know what Dory says? She reads the sign, and she says, escape. That's spelled just like escape. Oh, I love that line. Escape velocity from the Earth is 11.2, yes, 11.2 kilometers per second, otherwise known as a whopping 25,000, about 25,000 miles per hour. That's the speed we have to reach if we want to do something cool like go to the moon or go outside the solar system. We've got to achieve at least that just to get away from the Earth. So that is escape velocity. The sun has its own escape velocity. I mean, it's wonderful to be able to escape from the Earth, or it might be wonderful, but if you want to escape the solar system, you have to not only escape the Earth, but you also have to escape the sun. And if you want to escape the sun's gravity, if you start at the Earth, if this is the sun and this is the Earth, and you want to escape from Earth and also escape from the sun and leave the solar system, that requires from the sun, from the 42.2 kilometers per second. It's more because we are also trying to get away from the sun, not just away from the Earth. If you were to start trying to get away from the sun at the sun, if you're in orbit around the sun, you want to leave the sun. Because you're so much closer to the sun, it's going to take a whole lot more speed. The escape velocity from the sun is, get this, 620 kilometers per second. All of these escape speeds assume this is the speed that you are given, like a slingshot, and then no further power is applied. You're not constantly firing your engines. You're simply firing engines long enough to get you to that speed, like firing the engine with my hand to get this bag going, and once it's going, I let go, the bag leaves my hand. Once this thing is flung out here at 42.2, they shut down the engines. Or if you're at the sun, once the object hits 620 kilometers per second, you shut down the engines, and that speed that you gave it initially is enough to take it all the way out forever. How far will escape velocity take you? Indefinitely. It keeps on going. Now, if you find my explanation to be inadequate, then please, oh please, oh please, and even if you thought it was adequate, read page 194, page 195, where Paul Hewitt explains it all so very nicely. No, you don't have to have all these numbers memorized. I would expect you to know that escape velocity from the Earth is 11.2 kilometers per second, while orbital speed around the Earth is 8 kilometers per second. And then just the general concept of escaping from a larger object is going to take more speed, or escaping from the entire solar system will require more speed than just, say, going to the moon, which would only take 11.2. There's more that could be said, but I will refrain from babbling any further about that. Paul Hewitt mentions on page 196 some fun facts about Pioneer 10, a satellite that was sent out beyond the solar system. It's still out there flying to this day. How far away is it now? I do not know. That would be an interesting study to look it up and find out. I'm sure the NASA website would tell us. But as of the writing of this book, let's see, Pioneer 10, when was it launched? It was launched in 1972, and it passed Pluto in 1984. It took 12 years for that thing to get from here to Pluto. It passed Pluto and kept on going, and who knows where it is now. Pretty cool. Is this one moment? If there is a particular speed that's required to escape from a planet or a star, and that would take it all the way to the end of the universe, in theory, if it doesn't run into anything, if there were no other gravitational forces giving it trouble. Theoretically, that would take it all the way to the end of the universe. Now, what would be the reverse of that? Remember, if I toss this bag up, the upward trip is like a mirror image of the downward trip. My launch speed here will be the same as my catching speed down there, just in reverse. So, if escape velocity will take it all the way to the end of the universe, what would be the reverse of that? What if I went to the end of the universe and dropped the object and allowed it simply to fall back to the Earth? Its speed when it hit the Earth would be 11.2, ignoring the sun. If we insert the sun into the situation, it would be 42.2. The maximum possible falling speed of an object is going to be the escape velocity required to leave that object. If it takes, and let's just stick with our 11.2 number here, if it takes 11.2 kilometers per second to get this bag to escape Earth, then if I were to go out to Pluto or whatever and drop it back to the Earth, the maximum possible speed that it could hit would be 11.2, the reverse of escape velocity. So as I always tell folks, just in case this ever comes up, if somebody says to you, oh, I went to the top of the Sears Tower, and I know it was illegal, but I stepped out there on the top of the tower and I dropped a penny, and I put my radar on that thing, and when it hit the ground, it was doing 20,000, or let's change that, it was doing 20 kilometers per second. 20 kilometers per second when it hit. No, it wasn't. Not possible. If you just drop that penny off the side of the building, the maximum possible speed something can achieve when it simply falls to the earth is 11.2. So you can say, you're a liar. It wasn't going 20 kilometers per second. Not possible. It can't go any faster than 11.2 kilometers per second. Not even taking into consideration air friction. So, all right, now, I've already posted on RenWeb part 1 of the review assignment. I now give you the review assignment part 2. Let's see, I believe part 1 is due Tuesday, March 17th. Tuesday, March 17th at noon, as already specified. And I guess I should remind you here what that assignment was. Let's put it on the board. Due Tuesday by email or Google Classroom by noon will be the following. Page. I hope this is what I put online. Page 198, numbers 1 through 4, 6, 8 through 10, 12, 14 through 18, and how far did I take you? 21 and 24 was the end. That's part 1, due tomorrow by noon. All right, well, due tomorrow. I guess that depends on when you see this video. There's no rule that says you have to watch this video by then. But this has already been posted on RenWeb. It's been posted on Google Classroom, and it's been sent to you by email as well. So you're fully responsible for this by noon on Tuesday. The new assignment is, this one will be due Wednesday. And Wednesday is what? 3/18 by noon on Wednesday. And that will be part 2. Part 2. Yes, by the way, we are working toward a test. And yes, we will in some way, shape, or form, we're just not quite sure how yet, probably just by video, we will be going over these assignments in detail. I suppose that'll be a video. So let's see, part 2 begins with number 25 on page 199. Page 199, numbers 25 and 27 and 31 through 34, 31 through 34, 36, 38, 39, 41, 42, 46, 47, and 49. Done. All right, so tomorrow I'll be posting a video that will be going over part 1 of the review assignment, and then I will post later, probably Wednesday afternoon, I'll post the discussion of the problems from part 2, and then we'll talk about how we're going to do the test. Just to give you a heads up, my plan right now is to email a copy of the test to parents, asking them to then print the test, or if they can't print it, they can contact me and make some other arrangements, or they can simply have you take the test from the images on the screen, on their screen or your screen. That works too. But they'll be expected to proctor the test, and then you will send me the results, the video, or not video, a picture of the results by email. Scan the results, however you want to get me the answers. Send it to me by email. Yes, I do know that this lends itself to all kinds of possible illegal activities, but I'm simply asking the parents to make sure that to the best of their own ability that everything is done properly and legally. So that'll be coming later. For right now, there's part 2, due Wednesday. You already have part 1, due Tuesday. And I suppose I've babbled long enough. So we're done, and thank you. I'll be talking to you again tomorrow. Have a good Corona break.